Hello everyone, this is the second module of presentation equipment. In this presentation, I would like to talk about guide wave testing procedure using magnetoselective sensor technology. The second module of equipment consists of 7 presentations. This presentation will talk about couplings, the foundation of the guide wave testing. The second presentation covers the guided wave systems and probes in general, comparing MSS and piezoelectric systems. The third presentation covers MSS principle and probe design. The MSS testing procedure for torsional mode generation and detection will be covered in the 4th to 6th presentation, with the 4th presentation opening with a direction control before starting the procedure. The MSS testing procedure has the following 6 steps. Step 1 is finding location and preparing pipe surface. Step 2 is preparing strips. Step 3 is installing iron cobalt strips around the pipe. Step 4 is magnetizing strips for torsional mode operation. Step 5 is connecting MSS probes and instrument. Step 6 is acquiring data. The 7th presentation will cover data analysis and reporting using GIM version 7. UT's biggest demerit compared to all other NDT methods is its coupling requirement. Among NDT methods, ultrasonic testing's single largest practical demerit compared to RT, MT, PT, or ET is its dependence on coupling. A UT signal cannot enter the test material at all without the effective mechanical path from the transducer to the part. Every UT technique lives with this limitation. Guide wave testing GWT is a UT method and inherits the same fundamental requirement: no coupling, no signal, no inspection. Everything else depends on the first, coupling. This is the main reason of requiring a detailed UT signal in guide wave testing report that includes a 2 to 5 feet small section of a pipeline. How do you confirm that whether the guide wave testing is properly performed with a good coupling without checking the detailed UT signal? This slide explains what kind of a mode the coupling layer carries. This information is very important to do proper coupling in UT and guide wave testing. The wedge in conventional angle beam UT probe sets the angle at which the wave travels once it is already inside the solid wedge. It is nothing to do with the coupling layer itself. The couplant between the wedge and the steel surface is a thin liquid film, and a liquid cannot sustain shear stress. So the disturbance actually crossing the couplant film is always longitudinal, regardless of the wedge angle chosen. Mode conversion into the shear wave happens at the steel boundary itself, governed by refraction and wedge angle. The couplant's only job is transmitting a longitudinal disturbance across a thin gap. Ordinary low viscosity gel coupling does this well. The ordinary UT uses longitudinal wave mode coupling. MSS has no wedge, no refraction step. The iron cobalt strip is driven directly in the shear against the pipe surface. The coupling layer between the strip and the pipe must be transmitted that shear motion directly along through the coupling. A low viscosity liquid cannot do this. The couplant itself must be highly viscous in order to carry shear stress. This is why MSS require high viscosity shear couplant, epoxy bonding, or mechanical dry coupling under press. The MSS guide wave testing uses shear wave mode coupling. Because angle beam UT uses its couplant to carry longitudinal mode, Even an experienced UT level 2 or level 3 weld inspector has no prior working experience with a coupling medium that must itself sustain shear stress. This is another gap in their training that needs refreshing. It is a physical requirement entirely outside what conventional UT practice ever demands of them. Treat every inspector, regardless of UT background, as starting from zero on this specific point. Because the couplant's ability to carry shear is inherently a mechanically near-solid property, it is sensitive to viscosity, and viscosity changes with the temperature. This is a direct physical basis for the rule. Shear couplant is unreliable on warm or hot pipe, and dry coupling is required instead above ambient conditions. A conventional UT probe is a small, local point contact transducer. Poor coupling at that single contact point affects one measurement. An MSS coupled to pipe over its full circumference strip area, both transmitting and receiving guide wave energy across that same area. A single poor coupling patch anywhere along that strip contributes background noise to every signal acquired through that probe, not just to local reading. One working principle worth stating explicitly to trainees is that importance of coupling quality may scale with the square of the coupling area rather than linearly, though this should be presented as a technical heuristic rather than proven relationship unless it has been tested directly. In guide wave testing, unlike a point contact UT, coupling is not a per measurement concern. It is a continuous cumulative one across the entire probe contact area. Single weak section of a strip contact degrades the entire data set, not just one reading. The noise amplitude relative to a weld or other geometric feature signal answers three separate questions, each covered on the following slides: how good the coupling is, what the true inspection range actually is, and whether real GWT analysis was performed at all. If a report does not show the background noise level at small section of a pipeline, none of these three questions can be answered by anyone reviewing it. In MSS data acquired with the encircling probe, the width of the initial pulse is a direct field indicator of coupling quality. Good coupled data has a narrow initial pulse. Because the vibration excited in the iron-cold strip is efficiently coupled into the pipeline and propagates away as a guided wave. A wide initial pulse with a trailing signal is the indication of a poorly coupled section of a strip. The vibration is reflecting back and forth between the two edges of 2-inch wide iron cobalt strip because that section is not actually coupled to the pipe, so the energy has nowhere else to go and lingers as a trailing signal. The inspection range is decided by two things: the nearest big geometric feature such as flange and the background noise level. If someone says the inspection range is 50 feet, the first question to ask is, what is the background noise level at 50 feet? If the answer is 2% reflection, then with the standard 2:1 minimum signal-to-noise ratio, that noise level only supports the finding defect of 4% cross-sectional area or larger at that distance, not smaller defect, regardless of what the client actually needs to find. Without the noise level stated alongside the claimed range, there is no way to check whether the claimed range actually satisfies the client's detection requirement. A stated SNR or amplitude number is a claim, not evidence, until its reference is shown. For example, if inspector reports a very high SNR value attributed to good coupling, the direct question to ask is, what reference amplitude and noise floor are this number calculated from? If no calibration reference is provided when asked, the number cannot be independently verified by anyone reviewing the report. An unverified number in a report is exactly what background noise reporting exists to prevent. This is the practical, checkable difference between GWT, where every figure can be traced back to a calibration reference, and the guideway showings, GWS, where a number is simply asserted. The visual proof of GWS is reporting with a one-page report with deck curves for 200 feet coverage. The verbal proof of guideway showing is saying that the software did when asked how the inspection range and attenuation were decided. Documentary evidence that GWT inspection was not properly performed by a Level 2 inspector includes not reporting an indication or weld signal's percentage reflection value, and not including a detailed UT image for that section. Who can believe the guideway testing report that does not include one detailed UT plot? Who can find any defect without looking at the detailed UT signal? We'll return to this distinction in much more depth in Equipment 7 when we cover data analysis and reporting.